Okay, so the next topic is gas jets and combustion of gaseous fuel jets. Basically, this is the analysis of diffusion flames. So, first we will do the laminar diffusion flames. So, this is basically laminar diffusion or non-premixed. Okay, so laminar non-premixed or diffusion flames. So, that is the next topic what we are going to see. Okay, so let us take the simplest case where we have a fuel jet, just fuel alone coming out of a port or a nozzle. Okay, port may be a circular pipe and only fuel is supplied there, and or it may be a nozzle, contoured nozzle. And let us assume that the circular cross section, we can also use other cross sections, say square, rectangle, etc. But most of the burners are of circular cross section, so we will consider circular cross section with a radius of r. So only fuel is coming out of a port or a nozzle which is having circular cross section of radius r, and the velocity at which the fuel comes out is the exit velocity, or what is the average velocity of is VE. Okay. So, we can understand that if it is a nozzle, we will get almost a uniform profile, or what we call a top hat profile. So, the velocity will be VE everywhere. Or if you have a, say, a port which is end of a long pipe, then a fully developed flow comes out of that. So, the maximum velocity will be 2 times VE at the center, and it goes parabolically to 0 value at the walls. So, that the average velocity will still be VE. So, this average velocity I call jet exit velocity. Okay, so this is the jet exit velocity which is coming out of this pipe. So, you can see this is the schematic, this is the end of the pipe or a nozzle, whatever it may be. So, there this comes out, the fuel alone comes out, and there is no reaction to be considered now. So, let us say a cold reactant is considered here. That means only fuel is coming out, and due to the momentum of the fuel, air is present in the atmosphere which is not moving at all. So, air which is present outside this jet is quiescent in nature, and the jet is coming out with the average velocity VE. So, in this case, basically how the jet actually gets into the ambient and how its velocity and mass fraction of the fuel, etc., are affected, let us see. So, the figure here shows the contours of two things. Basically, first one is this part is the center line velocity, that is Vx is the, so there are this is an axisymmetric jet. So, you have two coordinates in cylindrical polar. The axial coordinate is x and the radial coordinate is r. Okay. So, in this coordinates, basically you can see that we are trying to plot as a function of the axial coordinate, we are trying to plot the quantities Vx0, V suffix x0 divided by Ve, that is the axial velocity at the central line. This 0 represents r equal to 0. So, at the axis, so this is the axis basically. This is the axis of the axisymmetric jet, and we are trying to plot the velocity along the axis. So, that velocity, but it is normalized by the exit velocity VE, which is the average velocity with which the fuel is coming out. So, Vx0 by VE, that or this mass fraction of the fuel. So, both will represent the same profile here. So, at the x equal to 0 position, let us take x equal to 0 position here as the exit of the port or the nozzle, that is x equal to 0, then x increases upwards. So, now at this point x equal to 0, you can see that the velocity is equal to VE, and so when you plot the axial velocity Vx 0 by VE will be 1. Similarly, mass fraction of the fuel will be 1. So, that is here. So, only fuel is coming out, so nothing else is there. So, fuel's mass fraction is 1 here. Okay. So, we can also say it is fuel stream. Even if you say a mixture of fuel, the fuel stream's mass fraction is 1, combine all the fuels together, or fuel plus a diluent can also come out, say fuel plus nitrogen, etc. So, that value is 1 here, and you can see that that continues for some height, that there is no change in the value of V x naught by V e or y f till a particular distance called x c. From x equal to 0 to a position called x equal to x c, there is no change in the center line value. This is the axis or center line. This along the axis or center line, when you try to plot, there is no change in the value of V suffix x naught by V e or the mass fraction of the fuel y f till a particular distance, say x c. Then what happens is, you can see a reduction in the value, and it reduces and goes. So, if you take a longer distance, it may asymptotically go to a 0 value. Okay, so, this is the axial profile. So, along the axis I try to plot. So, axial profile along at the plotted at the axis, basically along the axis. So, this is one thing. So, then the shown in the right hand side is the radial profiles at axial positions. So, for example, this first graph here is the radial profile of again the same quantities Vx by Ve. The axial velocity component is Vx, radial velocity component will be Vr. We are not touching that now. Axial component of the velocity will be very predominant than the radial component. So, I take this value Vx by the, and again normalizing that by the average exit velocity Ve. So, Vx by Ve, or no, I am plotting the Yf value. Now, at this station, that is x equal to 0. So, this is plotted at x equal to 0. So, the radial profile of this these two quantities are plotted at the axial location of nozzle exit or a port exit, which is x equal to 0. You can see that so this is the value of R. Okay, this is the value R. So, the value remains 1 and goes to 0 at R. Okay. So, at the value of R, it goes to 0. So, this is the profile you get, because you can see that. So, now again what we have seen assumed here is this is a fully developed flow. Basically, it is a uniform flow which is coming out. So, that is what the assumption. So, in the uniform flow, you can see that the values of Vx by Ve is 1. Similarly, mass fraction of the fuel is 1 and it goes 0 at the R. So, after that nothing is there. So, it goes 0. After, when the radial direction value is greater than the radius of the port, then the value goes 0 here. So, obviously, there is nothing coming out of that. So, it goes 0. Now, you take another location. So, this is another location, say I will say x equal to x1. At this, I try to plot the radial profile. You see now that as per this, the velocity has decayed to some value. So, Vx by Ve will be has decayed to some value. So, this will be the value. So, this value will be the center line value at the, this is the R equal to 0. So, this is the axial value, and it goes to the 0 value at a particular distance. So, asymptotically it goes, okay, at a particular distance it goes 0. Both Yf starting from this, you can see that the value is not 1 here, because there is a decay at this location of x equal to x1. You have already seen that the center line has decayed. Center line will have the maximum value, basically you can see center line has the maximum value and goes to 0 here, and radially it goes non-linearly to 0. When you take another higher location, so x equal to x2 here, you can get the similar type of profile you are getting, but the values are different. More decay has happened to both Vx by Ve at the center line as well as Yf at the center line, and from that starting that as a having that as a maximum value, it again decays, and it takes somewhat longer distance, radial distance, to go to 0 value. So, these are the radial profiles. So, let us discuss the characteristics of this jet. Okay. So, you can see that the point at which it goes almost to 0 value increases with x, correct. Again, the center line maximum value is decreasing of these quantities, plus you can see this here immediately at the radius of the port the values have become 0 in this at x equal to 0, but as x increases the value goes 0 at a longer radial value. So, this you have to understand. So, this when you try to join here, basically this, that is what is shown as the jet edge. When you attempt just trying to join this, so that is qualitatively shown as a jet edge here. Okay. Now, in the location where the mass fraction or Vx by Vx naught by Ve remains almost the same here, like remains constant. Okay. That I have indicated by a triangle here, red color triangle. This is nothing but the potential core of the jet. So, these are the definitions. Let us see more characteristics the next slide onwards. So, close to the port or the nozzle opening or the jet exit, what we call a potential core is seen to exist. That is that red color triangle what we have shown. So, here the effects of viscous shear or diffusion are absent, okay, are not present. Okay. So, here see when the jet goes out, it has some viscous effects, so by which it actually pulls in the atmospheric air inside it. So, that action is not felt until the distance of xc here, this xc, which is called the potential core. So, we can see that the values in the center line, basically the values are unchanged from the what is the exit values. Okay. So, here what happens, the velocity and the mass fraction of the gas, fuel gas remains constant exactly at the in-port values, whatever it comes coming out of the port, that is what is seen here, and is also uniform. So, we actually have assumed a uniform profile here for the velocity, so it is coming out as uniform. Now, this is first point, first important characteristic of a free jet. This is called a free jet. So, why this is called a free jet? Because this is the jet which is coming out of the port or the nozzle expand into a infinite atmosphere where there is no movement of any the atmospheric air. So, atmospheric air is stationary and that is trying to enter into this still air. Okay. Now, the another important characteristic of the free jet is the initial momentum of the jet is conserved. So, that means, okay, going back at any location, see for example, this is the exit of the jet, the nozzle. Okay. So, x equal to 0, at x equal to 0, the jet momentum will have some value. At any location if you take, see for example, I go to the x equal to x1 here or x equal to x2 here and so on, and try to see the momentum, integrate in the radial direction the momentum, that will be same as the initial momentum at the exit of the nozzle or the port. So, the momentum is conserved, momentum of a free jet is conserved. So, the initial jet momentum is conserved, that is very important. Okay. So, now this is for free jet. Please understand, if there is a confining walls or anything present, then this may not be applicable. So, only for the free jet the jet momentum is conserved. Then as the jet issues into the surrounding air, actually which is stationary basically, its momentum is transferred, some of its momentum is transferred to the air. Okay. That is why the velocity is decreasing here. So, after the potential core region till which there is no interaction, the viscous effects are not felt. So, after this point you can see that the velocity actually decays. This is due to transfer of momentum from the jet fluid to the air. So, that means it actually gives a momentum, so it spreads. So, the spreading is because of the transfer of momentum from the jet fuel to the atmospheric air. So, velocity of the jet decreases because of the momentum is transferred. So, why I am saying this? Because you can see that jet momentum is conserved, velocity is decreasing. So, momentum is conserved because of the addition of the mass. That means the air entrains into the jet, so that the mass actually increases at any station. So, if you see the exit of the nozzle or the port, you will see only fuel is present there. You take x equal to x1, the next station in the higher point, then you will see that there will be some air also which has joined in this, within this jet, within the jet edge boundary, the air also has come in now. Air has come. So, mass is added, but velocity is decreasing, mass is getting added due to the air entrainment from the surroundings into the jet. This is due to the momentum exchange and the viscous effects basically. And so, mass is added velocity decreases but momentum is conserved. Okay. Now as I told you, the subscript E denotes the exit condition, and the Vx is the axial component of the or the x direction, axial velocity component. Okay. Now the mass of the jet fluid is conserved. Please understand, jet fluid is the gas, the fuel gas which is coming out. So that should be conserved. Okay. So that another important point is this. So this mass has to come. See, mass, the total mass may increase. That is mass of the fuel which is coming out plus the mass of the air which has entrained, that will increase at any x location upwards when you go upwards, but the momentum is conserved because the velocity decreases, momentum is conserved. Then if you only take the mass of the fuel here, because there is no reaction we are considering, correct? Considering no reaction, the fuel, what is the mass of the fuel at this x equal to 0 location, that will be same if you only consider the mass of the fuel at x equal to x1 or x equal to x2, it will be the same. So the mass of the jet fuel or the jet fluid is conserved. So we can write at every station, I am just trying to integrate. So going in the radial direction, okay, radial integration starting from the axis, that is radius equal to 0 to I go to long value of r. So r tending to infinity. So I will take say many times the jet diameter. So jet diameter is say 2 times the r, the radius of the port. Now I take say 50 times something like that. So very big value of r I will take, try to integrate this. So this may be say 100 times r, something like that. Okay, r is the radius of the port. Now when I do this, the density, why density is changing here? Because not only fuel, now air also is added. So density at every point, at every radial location and axial location. So given at a particular axial location, if you want to fix x, then at least the radius density increases. Similarly, velocity will change. So velocity square. So rho v square represents that the momentum r into dr, 2 pi r into dr, that will be the area integration here. So if you integrate it, that should be equal to this at any x location will be equal to the initial jet momentum rho e, that is exit density, the density of the x equal to 0, v is the average exit velocity square, pi r square is the area of cross section, that is defined as the initial jet momentum Je, initial jet momentum. So that is conserved. We have seen that this is going to be conserved. At any x location, if you do this integration, you will see that that will be equal to Je, which is equal to rho e ve square into pi r square. So this is about the thing. So mass is added, velocity decays when you go to increased x values, but the momentum is conserved. Similarly, the mass of the jet fuel is conserved. So these are the two equations which we have to understand. Okay. So next is at any axial location x, the velocity or the mass fraction is maximum of the center line, that we have seen through the profiles, correct. Here we can see the at any location at this point it is maximum, and it actually stays in the exit of the jet, it stays for some time, then decreases to 0 rapidly. But if you take any other location where the decay has started, after that starting point of the decay, if you take any location, say x1 here, you can see that it starts at a maximum value at the center, then slowly decreases, non-linearly decreases to a 0 value. Similarly, at higher location, it takes little bit longer radius to decay to 0 value. That is what is indicated by the jet spread. So at any axial location, velocity or mass fraction is the maximum at the center line, because you can see that the core of the fuel is coming out of this, and entrainment happens from the periphery of the jet. So it decreases in the radial direction as we have shown in the profiles. Okay. So this is the profile, but you can see that the profile, even though you can see that the profiles are different here. So for example, the maximum values are different, the radial position at which this go to 0, these values goes to 0, that is also different, but these are called self-similar profiles. We will just come to that later. Okay. So this is the characteristic, starting with the maximum value of the center line, decaying to a 0 value or a very low value at the given distance from the center line, radial distance from the center line. So that is the characteristic radial profile of the velocity or the mass fraction. Okay. Now Actually no, it, as I told you, it asymptotically goes to a 0 value. That means it takes longer radial distance to get to the 0 value. So it is not easy to really trace that 0 point. So what we now generally do is we seek a radial location, or we try to evaluate a radial location at which the jet velocity decays to half of its central line value Vx0. So if you go to the profile, if you take the maximum here and it goes to 0 like this, it goes to every asymptotically it goes to, so this is radius and this is the Vx naught here, this is Vx naught and this is the Vx profile basically. So you can see that from starting from the Vx naught value, central line value is the Vx naught, it decays to a low value at far field. So instead of going till infinity or a very long radial location, we can define, see for this value, so let us take this as Vx 0 by 2, half of the central line value, and see what is the radial location at which it is attained. Okay, so this location is called R half or suffix half, that is called jet half width. Okay, so starting from the central line value in the radial direction, the value of the velocity decreases non-uniformly and goes to a 0 value at a very long radial location. So instead of tracing that 0 value, we are trying to take the radial location where the velocity has decreased to half of its initial, the central line value. So if central line value is Vx naught, the radial location at which the central line value has reached to half of its value Vx naught by 2, that location is taken as the jet half width or suffix half. Okay. So this is another characteristic of a jet, a feature. Okay. So this jet half width also you can see at a given radial location, it will have some value. So it is a function of x. This is a function of x. So at a lower x location, it will have a smaller value. When the x location increases, it will also have a larger and larger values. So like a jet edge, where the velocities go to almost 0 value, the jet half width also increases with the increasing x axial distance or the x value. Okay. So you can see here at this location, say x equal to x1, you will see the half value will be somewhere here. So here at this location you are going to go to here somewhere. So you can see there is an increase in the half jet half width. So there is an increase. So it also spreads, that jet half width also increases with the axial distance, like the jet edge. Jet edge increases with the axial distance. Similarly, the half width also increases with the axial distance. Okay, so that is one of the another next characteristics is this jet half width. So first is the radial profile, which exhibits a maximum value at the central line and goes asymptotically to 0 value along the radial direction. That is one characteristic. Second characteristic is the jet half width. Okay, where the from the central line value the velocity has decayed to half of its central line value. Okay. Then we go to another definition, which is the ratio of jet half width to the axial distance. X is termed as the jet spreading rate. How far the jet spread? That is very important characteristics. Okay. So R half at a particular x. So if we calculate this R half as a function of x, no, so R half at a particular x location. So this ratio is called jet spreading rate. Correct. So this varies. So R half is lower at a lower x. So as x increases, R half also increases. But this ratio R half by x, that will indicate the jet spreading rate. And the angle, so if you go to this, again go to this figure. So this angle, what we are talking here, this angle is got by taking tan inverse of this ratio. That means the angle alpha, that is called jet spreading angle. Alpha is nothing but tan inverse of the ratio of R half by x. So the ratio R half by x is the spreading rate. Tan inverse of this value will be the spreading angle. So, these are another two important characteristics. So, potential core till which the viscous effects or diffusion effects are not important, and there is no change in the value in the central line than what we saw at the exit for both velocity as well as for the mass fraction. So, that is one of the important characteristics, potential core, the formation of potential core, momentum being conserved, jet fluid mass being conserved, then the radial profile exhibiting maximum value at the central line and going asymptotic to 0 at further locations, radial locations, then definition of half width, then you can see that this jet spreading rate R of by x and spreading angle. These are all important parameters which we use to analyze a jet. Okay, now, so what is the use of defining R of etc. or, because if you try to plot, as I told you, if you go to this depending upon the value of x, say x1 or x2, you get the profiles with different maximum value. Okay, our central line maximum value here is much less than 1 when you compare to a lower location x1 where it is close to 1. Okay, so we can see that the maximum value itself changes. Similarly, the value at which the R of occurs or the value at the jet edge, that also is different for these two profiles. Okay, so if this is the case, then this is a two-dimensional problem then, correct. So, we have to really take into account of both axial and the radial direction to solve this problem. Okay, but if we try to plot Vx at any radial, so take any axial location. So, Vx along the radius divided by the central line value at that x location. So, I fix the x location. So, at a given x location, I know what is the maximum value of the velocity, axial velocity, which will occur at the central line. So, that is known to me, Vx naught. So, that is taken for normalizing this, and now I try to plot the axial velocity along the radius. Okay, so, I normalize this at every x location. I try to normalize the velocity, axial velocity with the central line value at that x location Vx naught. So, that I plot in the y axis. In the x axis, radius should come, but I do not plot radius alone, I plot radius divided by the half width, R by R half, R suffix half. If I do this, then all these profiles collapse to one profile, which is called self-similar profile. Okay. So, that means if I plot Vx divided by Vx at the center, here you get R by R half, then you get only one profile like this. Starting from 1, you get one profile like this. So, at every location, at any x location, you will get only one profile like this. So, that is called self-similar profile. Okay. You may remember that for boundary layers, if I plot u by u infinity, see for example, boundary layer, if you take, see boundary layer, this is u infinity with a flow which is coming in, and boundary layer is formed, and if we take any x location, okay, I get this boundary layer profile. So, when I try to plot u by u infinity versus say this is y direction and this is x direction, so versus y by del, which is the boundary layer thickness, then this profile is similar, correct. So, similar to that, when I plot Vx, that is the axial velocity along the radial direction, normalized by the maximum value at that x location, which is the central line value Vx naught for a given x location, that versus the radial direction divided by the half width at that x location, because please understand that R of also is a function of x. So, I plot this. So, at a particular x location, axial location, I will get one value for Vx naught. By the decay, I know that. Similarly, I can calculate the half width at that location. So, when I use these two quantities, like for example, u is normalized by u infinity and y is normalized by del, that is the boundary layer thickness, but boundary layer thickness itself will vary with x. Similar to that, r of what I am plotting here, z of it, that will vary with x. So, at a given location there is a particular value for Vx naught, center line velocity, and also for r half. When I use that and plot, I will get one profile. If I plot for every x location the same thing, then I will get the same profile, which is called self-similar profile. Okay, now the problem is reduced to a one-dimensional problem. Do you understand? So, that means that if I do not really need to account for the x direction now, because at every x location, if I think of a similarity variable, then I can go for what is called a similarity analysis, like what we normally do for a boundary layer. Okay, self-similar profile can be done with this. So, we have to define variables carefully and do it. So, that is what we are going to do this. I am not going to go for the entire derivation.